Hello again, and welcome to our last presentation of At the U at the Center. I'm Laura Peterson. This series comes to you from the Osher Lifelong Learning Institute at the University of Minnesota. OLLI is a learning community for people 50 and over who are curious lifelong learners. We offer hundreds of non-credit courses a year. It's the best bargain in the Twin Cities, plus other ways to get involved, like special interest groups and volunteer opportunities. I want to extend a warm welcome to our OLLI members who are on this webinar, as well as our guests. Today's presentation is titled Catastrophic Collisions: Ancient Meteorite Impacts Buried Beneath the Twin Cities, and an overview of significant meteorite impacts throughout history, with Julia Steenberg. Ms. Steenberg received her master's in geosciences from Idaho State University and is a Phanerozoic geologist at the Minnesota Geological Survey, an affiliate of the University of Minnesota. She served as president of the Minnesota Groundwater Association and is now serving on the board of directors for the Minnesota Groundwater Association Foundation. She belongs to the Geological Society of America, and her research interests include geological mapping, Paleozoic sedimentology and stratigraphy, hydrostratigraphy, carbonate sedimentology, and structural geology. Ms. Steenberg, the floor is yours.
Well, thank you. Happy to be here. I'm going to have a lot to tell you about geology today, sort of the regional geology of Minnesota. That's my background. And also about this really important discovery that we found. So there's a lot to go over. So I'll start off with an outline so you can see where we're going today. I'll start off with the Geological Survey, what we do, the mapping that we do here. And then we'll go over an overview of meteorite impact events on Earth. And then we'll talk about the regional and local geology quite a bit, because this structure that we found is buried. And really the only thing that clued us into its existence is that it was out of the ordinary for what should be there. So we'll kind of go over what should be there first, and you can see the structure and the evidence for it after that. And then we'll go through a comparison from our structure, our proposed structure, to some other important impact structures around Earth. So that's where we're headed. I should say, if any of you are interested, that photo on the right is at the Pine Bend Bluff Scenic and Natural Area owned by the DNR, looking out east towards the Mississippi River, towards Hastings, looking towards Hastings. So that's the site in Inver Grove that we're going to talk about today. All right, the Minnesota Geological Survey is part of the University of Minnesota. We are specifically part of the School of Earth and Environmental Sciences and the College of Science and Engineering. And we do have our own building off campus, kind of right by 280 and 94. We have a map sales office. All of the maps and reports and things that we have for sale for paper copies are also all available digitally for free on our website there. So you can browse through any of our geology past reports if you have interest in geology. A little slow here. We'll go like that. And then we just have a host of other general information on Minnesota geology as well. If you click around on our website, you can find all sorts of fun things. The main, I guess, bread and butter of what we do here is geologic mapping, and our main program is called the County Geologic Atlas. And the County Geologic Atlas is done both by us, the Minnesota Geological Survey, in conjunction with the Department of Natural Resources Waters Division. And MGS, we investigate the geology and produce maps and what are known as GIS products, sort of digital map products, describing the geologic framework. And that's the geologic framework consists of anything from the first few meters of sediment all the way down to thousands of feet into the deeper, older Precambrian rocks. And the DNR investigates the second aspect of the County Geologic Atlas program, which is the groundwater, the chemistry of the groundwater, the quantity, and pollution sensitivity. So they produce what are called Part B geologic atlases. So you can just see a variety of those, what they look like in paper form on the lower left there. And then some of the GIS layers associated with what we create. And then our status map on the right. We've got a lot of counties underway, and you can see in the yellow sort of the areas where we're working currently and trying to finish up. So on to impacts on Earth, right? Nearly 200 confirmed global sites on what's known as the Earth Impact Database. And structures range from just small circular craters of just a few meters to large complex structures as much as 160 kilometers across. So there's a whole host of different structures identified on Earth that we scientists have to learn from, but they're quite rare, right? Just 200 of them. They range in age from quite old to 2 billion years old, and all the way to quite recent, just 14 years ago was one that fell in Peru. And craters, out of the whole 200 or so, about a third of them are buried by overlying sediments, which is the one like we have in Minnesota. And some other important large craters that are buried also include Chicxulub and the Chesapeake Bay structure. So Earth has many fewer craters than the moon or other planetary bodies, right? You can just look up at the moon and kind of just get that from visual looking at it. But and that's mostly because the geologic processes on Earth erase craters with time. Earth has high erosion rates and plate tectonics, and those are things that the moon and other planetary bodies don't have. You saw on that previous map, most of the craters are on continental crust and not in the ocean, although some do exist in the ocean. The ocean ones are harder to find, obviously, but the ocean crust is actually quite young compared to the rest of the continental crust on Earth. So that's another reason why they are spread more onto the continents than the oceans. And there's been calculations done based on how often craters are produced and Earth's erosion rate. And those calculations tell us that there are several more craters on the small side left to be found, but that we believe that most of the larger ones are accounted for. And that's just kind of shown by the density of confirmed craters on this graph and the smaller density in this zone where the diameters are about 3, 4, 6 kilometers or less. Impacts are recognized as a major factor in our planet's geological and biological history. They generate instantaneous geological structures. These literally take minutes, we think, to produce, even seconds for some of the smaller ones. You just don't get geologic forces like that anywhere else. And they also are known to be associated with regional or even global ejecta layers. That's sort of that dust cloud that gets, everything gets vaporized and brought into the atmosphere and then falls back out as what's called an ejecta layer. Those can be found all over the world from some of the larger structures. They've also known to produce what's known as a large igneous body, such as the Sudbury, Ontario structure, where forces were so high and the temperatures were so great that it literally melts the Earth's continental crust and creates a new igneous rock in its place. And many are also known to be associated with economic mineral and petroleum deposits, such as the copper nickel sulfide deposit at Sudbury. And then the fun one, some are known to be associated with major biological extinctions, including the Chicxulub, Mexico impact structure that's known to be associated with the end of the dinosaurs. So there's 3 stages of impact cratering, right? There's the initial contact and compression stage, we call it, where it's estimated that the average velocity of one of these space rocks coming to Earth is just a mere 17 kilometers per second, which equates to 38,000 miles per hour. So these are incredibly fast, forceful objects, right? And that initial contact just takes tenths of a second to really obliterate everything and create a structure. In terms of energy, these carry, just an object only a few meters can carry the kinetic energy of an atomic bomb. So these are big energy features. And then there's the excavation stage, sort of the expansion of the shock wave after it hits, right? And those shock waves travel as well kilometers per second outward from the impact zone. That's when the cavity opens up, things are deformed, the rock's shattered and melted, and then it creates sort of a shape that's usually a little bit wider than it is deeper. And then there's the modification stage where sort of gravity drives the collapse of that crater. And again, all these things just take several seconds to complete. And based on that cavity that's created at the end, we sort of classify these things into a simple crater or a complex crater based on morphology that you see. So again, these things have devastating heat, and gases can be released from vaporizing these large amounts of rocks. Target rocks is what we call it when an impact hits, and they produce major environmental effects. So here's that classification between a simple and a complex crater. So you just can kind of see, based on models and studies from all the other craters on Earth, you can kind of put together this comparison. And the simple crater would be like on that picture I showed a few slides back of Barringer or Meteor crater, where you have sort of a simple bowl shape opening up. And a complex crater is just a little bit different. It has terrace rims, so you can see those along the edges, and an uplifted center where the rocks from deeper into the Earth have been brought up. And breccia also fills sort of the areas within the crater. So to be accepted in the geologic realm for having an accepted crater, you need to show that you've got shocked metamorphic effects in minerals. There's other ways to create a large hole in the Earth's crust, such as a sinkhole or some sort. If you can document that you have shocked metamorphic effects in minerals that only happen with such great forces, then that's what you need to have an accepted impact structure. And those can be things like shatter cones. You can see the pattern there, sort of this feather-like pattern where the rock structure actually, from the force of the impact, actually sort of breaks, cracks, and then reforms into that pattern. And there's other features, planar features in quartz grains are very small features you can see here called shocked quartz. And I'll show you some examples of that later. But it's just from great pressures that the quartz grains can produce those shocked layers like that. And we call them either planar fractures or planar deformation features based on the spacing of those small fractures. And there's other things too, high pressure, what are known as polymorphs, which is the same chemical composition, but a different crystal structure in these minerals at a real fine scale under the microscope. Basically, crystals changing. Quartz can change to coesite and schistosite, and carbon can change to diamond, and so on. And then the other things, impact melt glass is also considered an impact criteria. Impact science today is focused on new findings. It's also focused on, just better understanding the mechanisms by which impacts produce these large biologic and geologic effects. It's focused on the chemical and mineralogical changes at that fine scale that occur during the impact event. And then studying, these impact structures to better find the complex mechanisms of how impact structures form on Earth and other planets. And, I think this was one of the questions posed, why do we care? And I think this is important to talk about the potential for impacts to serve as analogs for other planetary surfaces. To be honest, I've been a geologist, interested in geology my whole life, right, since I was a kid. But you don't really think and geologists are guilty of thinking at a longer time scale than a lot of things that go on everyday life. But I don't often think on this time scale, right? The potential for impacts to serve as analogs for other planetary surfaces, and understanding this impact risk and mitigating of such risk. And, it was just last year that the DART mission went off, and we've proved that we can actually alter the course of a space rock if we need to, so these are things that that the government and the space program is thinking about. And it's just important to understand the formation and the process of how our planet came to be. And our planet came to be just basically by a series of long accumulating impacts at various scales. And of course, there's an importance of impact craters and the cratering process in forming and controlling the location of recoverable resources, both on Earth and on other planets or the moon. And then they're just so interesting to study, really. And you look around at the map here, it shows that there actually are quite a few around us. This would be Minnesota's first documented crater. We haven't had one documented yet. You can see Iowa, Wisconsin, North Dakota, and Canada all around us. They had us beat. This structure is in south in Inver Grove Heights, about 11 miles from St. Paul. So it's not that far away from maybe where you are today. And according to based on some of these other ones around us, I'll talk more about these specific ones in a little bit later, but they all range, even the ones all around Minnesota range from just a few kilometers and on the small side to a few up to 35 kilometers or so. Those are getting to be on the medium to large size. And they occur all throughout, the geologic record at different time periods. This MA on the right-hand side here tells you how old they are in millions of years. And they hit both sedimentary rocks and they hit crystalline rocks, and those just form, different types of craters and different structures associated with them. So let's get into the geology a little bit more on Minnesota. So again, we said this is pretty within the metro area, and that is Paleozoic rock. If you got rid of all the Quaternary, which is the glacial sediments. If you removed all the glacial sediments, sometimes those are several hundreds of feet thick. If you remove them all, this is what you would look like. This is what the Earth's Minnesota surface would look like. It would be what are known as Cambrian or Ordovician rocks, aged rocks, and you can see how they're layered there. They're sedimentary rock packages representing sort of environments of ancient seas. And so the older ones, the Cambrian ones, are in yellow, and then the Ordovician sequences in blue. And the Paleozoic rocks of Minnesota are of generally three main rock types. There's just your basic quartz sandstone, which you can see in the image on the left here, nice white pure quartz sand. And then we've got sort of a finer grained shale, silt, and fine sand rock type. You can see the shale, this is gray shale here. And then we've got what's known as carbonate, or either limestone or dolostone. Usually forms, it's calcium carbonate. It is this sort of tan or gray crystalline limestone looking like rock. And you can see the Ordovician sequence is mostly Cambrian, with the exception of the St. Peter sandstones, kind of packaged in the middle there. And the Cambrian rocks in Minnesota are mostly sandstone and what's known as the fine sandstone and shale facies. And this is our geologic column on the right here. And it just kind of shows you if you were to have them all, if they were all stacked up on each other, which they rarely are because they've been eroded into by the glacial sequence. But if they were, you'd have a series of older Precambrian sediments at the base, and then you'd have the Mount Simon sandstone all the way up through, at least in the Twin Cities area, the Decorah Shale. So it is really a layer cake that we have to work with in the Twin Cities and in the Paleozoics in general, in the whole region in Minnesota and Wisconsin, Iowa, and Illinois. These are pretty straightforward. We like to call them just a predictable package or sequence of strata. And, you know, starting down at the Mount Simon all the way up through the Decorah Shale again. And this is a cross section taken kind of east to west across the, or west to east across the Twin Cities. And you can see these colors through the middle here. Those are the Decorah and Platteville formations, and they form in the middle, and then the older rocks form along the sides, and that's just associated with the basin. We call the Twin Cities Basin, where the older rocks are on the edges and the younger rocks are in the middle. And you know, they're generally fairly uniform in thickness as well. There's sort of a general thickness guide here. Some of the rocks are several hundred, some of the formations themselves are several hundred feet thick. But they generally have a similar consistent thickness across the region and even across the whole state in some cases. So beneath that Paleozoic sequence of sandstones, limestones, and shales, we have the older Precambrian rocks beneath that. And in the Twin Cities, there are the Paleozoic sequence is about 1,200 feet thick if the whole thing was exposed. So we're talking now about rocks that are, around 1,000 feet deep or so. And we don't know a lot about them in terms of well data. There's some core, that's what you see here in these photos of those rocks, but not a lot of core. We just don't have reasons to drill deep into these rocks very often. So the data that we have on them is based on what's called aeromagnetics. So you can see that when we like to call that, it's like an MRI of the state of Minnesota. What you're seeing there is the whites and light pinks, and pinks are the rocks that have a high iron content or are more magnetic than the blues and the green rocks. And so what you're seeing there are these deep Precambrian rocks that sort of form this circle are the basalts associated with the mid-continent rift. And then in other areas, we've got a package of shales and sandstones that are just the sedimentary rocks of the mid-continent rift. So I'll go through some of those Paleozoic rock layers just to get you familiar with the sequence. Starting from the top, so here's the Decorah Shale. The Decorah Shale at Lilydale, maybe some of you have been there in the past, where you can be able to do some fossil hunting there. The Decorah Shale is exposed, right around here, if you can see my cursor. And then the Twin Cities, the river valleys are where we have most of the exposures of the bedrock. Everything in sort of a red pattern here is where we have rock exposed. So you can see it's limited mostly to the river valleys and a little bit in southeast Dakota County where there are where the glacial sediments are thin. And so you can see this is the Platteville with the Glenwood and the St. Peter. So those are exposures you see kind of all throughout the Mississippi River Valley and the Twin Cities. And I should have said this from the get-go, but we came across this discovery while doing that County Geologic Atlas mapping project for Dakota County. So that's hence all the Dakota County maps I'm showing you. And here's the Shakopee Formation. Maybe you've seen the Shakopee Formation. There's a really nice park in Hastings called the Vermilion River or Vermilion Falls Park. That's where this photo was taken of the Prairie du Chien. And there's a bike trail not too far away from there where you can see some nice Prairie du Chien exposures as well. Just kind of a tan carbonate with not a lot to see. But it's a unit that's fairly thick, several hundred feet thick. Occurs below the St. Peter sandstone and above the Jordan sandstone. So it's an important unit. It provides sort of a nice, well, it's the uppermost bedrock through a lot of Dakota County. Everywhere in the blue or dark blue you see here is where the Prairie du Chien is the first bedrock beneath the glacial deposits. And then the last unit that we have exposed in Dakota County is the Jordan sandstone. And so here's a photograph of just the uppermost Jordan sandstone beneath what this is the lowermost Prairie du Chien or Oneota Formation. And that's exposed along the river valley, kind of near Hastings as well. And then that's it for exposures. There are rocks deeper, but they are not exposed at the surface. So in order to get familiar with the rocks and map them that are deeper, we need to use what are called geologic cutting samples. And so these are samples collected while water wells or other wells are getting drilled. And then we house and store these cuttings at our office here. And you can see they're sort of usually collected in 5-foot intervals and then put in boxes and washed and then put in boxes, envelopes within leather boxes. So that's our cuttings library at the MGS, and the units below the Jordan sandstone include the St. Lawrence, the Tunnel City, and the Wanawak, Eau Claire, and Mount Simon. So you can just kind of already just with your eye sort of see which ones are the sandstones, right? The Wanawak and Mount Simon are the quartz sandstones. The Tunnel City is a glauconitic fine grained sandstone, so it almost looks like salt and pepper. I'll show you some better pictures of these units as we go along. And the Eau Claire is more of a shale to a fine grained siltstone to a shale. The St. Lawrence as well, fine grained siltstone mostly, and can have some glauconite in it, but usually not as much as the Tunnel City. The glauconite, I should say, is a mineral that looks like these little pepper grains in here that occurs in our Paleozoic rock formations. So this is now zooming into sort of the northern portion of Dakota County. You can kind of see its outline here, and basically looking at the metro region at that view. And this is just to show you that this area has a lot of subsurface data, right? We're an urban, industrial, residential area, kind of on the outskirts of the suburbs. And we've got a lot of subsurface data because of all the development that's gone on in the area in the past. And we have a variety of different databases that we continually update and work on to store all this geologic data. And one of them is just what's called the water well database that we sort of work on with the Department of Health. And anywhere there's a black dot is where we've got a record of a well. And every well, every well since the 70s, when the Clean Water Act was passed, has to have what's called a well record. And the well driller has to describe what the geologic materials they found or were drilling through at depth and how thick they were and so on. It's got a variety of other things like the location and then the well construction information. So that's one of the data sets we use to sort of parse out the geology beneath the surface. And then anywhere there's sort of a yellow cross or a T, that's where we have geologic cutting samples, such as what I was telling you before, or housed in the cuttings database. And then anywhere there is a square, we have what's known as a geophysical log. And here's an example of what a geophysical log is. That's just tools we have that are mounted to basically a truck or a van that anytime a new well gets drilled or their pump is being pulled because it's being worked on, we sometimes get the opportunity to go in these wells with our tools and then it's just basically measuring the natural gamma radiation in the rock layers, and the shales and the finer grain units have more feldspar minerals in them than the quartz sandstones or the carbonates. And so you basically can get just a relative sense of which ones are more shaly, have more feldspars, versus which ones are more quartz sandstone rich. And we have so many of these geophysical logs that having one, you can correlate very nicely from place to place and kind of match out the rock layers beneath the surface. So as I was mapping Dakota County, things were relatively straightforward. I kept ignoring this one site that didn't quite make a lot of sense with the data I was working with, and finally got everything else done and had to sort of hone into this site and make sense of it. And I just had this series of about 30 or 40 wells that just didn't match, where they were calling sandstone, maybe it was a funny color being described that usually isn't described, or they were calling it sand when it should have been limestone, and things just weren't quite making any sense. And that's just within this region here. And if you looked on the aerial footage, that's basically this region here. That's that Pine Bluffs scenic and natural area that I described. It's just, there's residential areas to the north. Otherwise it's pretty industrial. Truck stops, landfills. It's just north of the refinery. It's adjacent to the Mississippi River. So it's an interesting site geographically. And the region was traditionally called Pine Bend, after sort of the historical settlement name for the site. So that's the name we're giving to this structure. So if we zoom into that pattern, that circular feature, basically this pattern here is going to follow here. And I'm just going to show you some geophysical logs. So I know you're not expert geologists yet, but maybe by the end of this hour you will be. But if we look from west to east, so this is Dakota County over here, and this is just across the river, Mississippi River, into Washington County. These are two wells, one's right here, and then the other one's right here. And this is the geologic interpretation for these geophysical logs. You can see some of the sand units. I have a low signature. Mount Simon has generally a low signature. It gets kind of shaly as you go up towards the Eau Claire. As you can see, these gray dashed lines and how they should correlate from place to place. So you can have geophysical logs several miles apart, several hundred miles apart, and really be able to sort of trace out which units are which units, okay? But we have this series of geophysical logs in the circle in the structure that don't make any sense. And that was one thing we were really struggling with as we were trying to do this mapping, is what's going on here? I mean, you can look at certain sections and sort of say, well, that kind of looks like that should be the Eau Claire, or maybe that actually looks like it should be the Alone Rock, but it's several hundred feet lower than it should be, right? These are all sort of hanging on elevation here. So this was part of the puzzle, sort of piecing these geophysical logs together. And some of these, three of them, well, the two on the outer sides, the ones to the west and east, those have geologic cutting samples to go along with the interpretations, and so do three of these others. So I'm going to walk you through two of these geologic samples so you can just get a sense of what they look like. The first one I'm going to show you is this one we call MGS number 704. So I'm going to show you, actually, I'm going to show you 3240 first. Sorry, that got mixed up. So I'm going to show you this one next. So this one, right out of the box, this is kind of what we do. We put them in these, take them out of the envelope, spread them out. And just right out of the box, it was striking, anomalous, right? We just don't get these deep red colors in the Paleozoic rocks anywhere in Minnesota. So the colors are off, and they don't really correspond to any of the expected units at depth. So again, in gray is what the expected unit should be. And this would be anywhere from the Jordan sandstone all the way down to the Wanawak sandstone. And the geophysical log doesn't really match what should be there either. So I'll take you through some closer looks at them. From the top, we have sort of a poorly sorted quartz sandstone with these cloudy, milky almost looking grains. And something that should be the Jordan sandstone, so it kind of matches as a sand unit, but the grains are the odd fractured grains kind of struck us as being not normal. And then we've got that deep red color came from rocks that look something like this up close, which is what are known as sort of feldspar, not just quartz, but it had some feldspar in it. It also appears to have pebbles of rhyolite and basalt in it, and iron oxide coatings. Those would be really odd to have anywhere in the Paleozoic rock sequence. And instead, they're more associated with those at great depths, which are those Precambrian rift sediment sandstones. So those are a bit odd. They are several hundred feet higher than the rift sediments, which should be at greater depths here. And then below those, we have what appears to be these more typical Cambrian strata, which shouldn't be below the older rocks, right? And those are sort of a coarse, more of a coarse, pebbly sandstone with some more of these fractured quartz grains. And then below that at depth, we had glauconitic sandstone with these little phosphatic brachiopods. So these little broken shells here is a brachiopods that are mostly associated, that are commonly found in either the Lone Rock or the Eau Claire, or what's the Lone Rock or the Tunnel City group or the Eau Claire sandstone. So that kind of gives us a key as, things are not where they should be in this section. And let me show you what these quartz grains look like up close. They're densely fractured. They're common in several intervals, not just the top, but they're common at depths too. You can see in the ones that are circled are the fractured grains versus the non-fractured grains. They're just a little bit more translucent. Here they are sort of under different light conditions, or you can see the typical quartz grains versus the fractured ones we also see. So both fractured and non-fractured ones are existing in the same sequence. And that, immediately said, wow, this is interesting. Most of the quartz grains are never fractured in any of the Paleozoic sequence. There are several geologic ways to fracture quartz. But what immediately caught our attention was the fractured quartz grains, and knowing that just our colleagues just to the south of us in Iowa had recently published a paper on their fractured quartz grains from a sandstone interval that under the microscope have what are known as planar deformation features, which are those very closely micrometer spaced fractures in the quartz grains that are really only, have to be formed under such high pressures that are really only known to happen during a meteorite impact or an atomic bomb. So we immediately sent out some of our quartz grains to get analyzed for what we call petrographically or microscopically, and we have what looks like pretty classic shocked quartz, where we have planar fractures and thin sections in several different orientations, 2 to 3 different preferred orientations. And here's another one where you can see a few different orientations of the fracture patterns in the grains. Here's sort of looking from farther away versus close up. And then these little dots along the fracture grain are what are called fluid inclusions. It's just sometimes makes it a little easier to find them. And I'm a mapper, I'm a Paleozoic geologist, I study these rocks, but I'm not an expert in impacts. I'm not an expert in shock quartz either. So we definitely sought help from the experts. We we asked a few experts that have published on shock quartz in the past, Ludovic Ferrer at the Natural History Museum in Vienna and Uwe at the University of Brazil. And they were quite pleased. They said, yes, you definitely have some planar features. And sorry, I'm just trying to move this. And you've got sort of these planar fractures, which are these ones on the left here, which are more further spaced fractures, about 15 to 20 micrometers apart with several different orientations. But again, those can possibly form in other conditions, not an impact event. What we're looking for are these ones, which are the much more closely spaced features known as PDFs or planar deformation features, which are really not open fractures at all in the quartz grain. Instead, they're just narrow individual planes of material very closely spaced. And then those are often decorated with what are these little dots along the fracture line here, which are which are the fluid inclusions, So those are pictures from our site, so sent by Ludovic. So we have some PDFs to work with from those quartz sand grains. And next, I'm going to show you a picture of the other set of samples I wanted to show you, which let's see if this one came out right. I'm going to show you this log right here. And that one is sort of the last one with all the shock quartz grains. That's kind of right in the middle. And then this one I'm going to show you is just to the south. So this is what the rocks look like up close. In this next log I want to show you, and again, things are not typical. They don't match what should be there. The geophysical log does not match what should be there. And instead we have phosphatic brachiopods in this glauconitic sandstone at the top. And then we've got a little bit more of that as we go down. And then below that, we have a sequence to almost 200 feet thick or so of just fine, coarse, mature quartz sandstone, which is pretty odd for the area. And then most of the time, the sandstone occurs right here for what should be called the Wanawak sandstone, which is only usually 55 feet thick or so. It never reaches thicknesses of 200 feet. So right away, that kind of struck us as being anomalous or different, not matching with the region. Below that, we have more glauconitic sandstone. And at the very bottom, we have samples of red and green shale, as well as carbonate-rich shale and siltstone, which are also very odd for the region, something we think may be related to those deeper Precambrian rocks. So instead of this gamma log, this is our interpretation of this gamma log. So this log is still the same. And what we think we're seeing based on the rocks is what's actually overturned rock, where the two Cambrian formations, well, the three, the Lone Rock, St. Lawrence, and Jordan, this is sort of your typical Cambrian sequence, but what we believe is that these older sequences are overturned on top of itself. So how does that happen? It doesn't happen in Minnesota. It doesn't happen in Minnesota, right? So how can we explain this hypothesis of this stratigraphy that would require over 200 feet of overturned strata? There are mechanisms, there are geologic faults in the region, what's known as either a reverse fault or a normal fault, right? These are near vertical geologic faults affecting the Paleozoic are common. Here's an example of Barn Bluff in Red Wing. It's kind of a classic structural geology field trip stop. It's not exposed as well as it was back when this photograph was taken, but you can see these green sandstones are juxtaposed right up against this tan Jordan sandstone. So that would be what a fault would look like, but oftentimes those are just vertical features and they would not we've never seen anything where a rock is basically folded onto itself. You can get that out in Western United States, but we just don't have those settings here in Minnesota. So instead, what we think we're seeing based on the shock quartz features as well as the overturned beds is what's known as an ejecta flap. So if you have a structure, a meteorite crater formation, basically it hits, things are blasted out, and this feature here basically just kind of the blast out and fall back is just what causes the ejecta to flap back. You can see this at Barringer Crater, Meteor Crater in Arizona today, where the sediments that used to be sort of overlying the whole thing have sort of been ejected up and fallen back on itself along the edges. So that's our hypothesis of what's going on here in this well. This has also been noted at the Manson impact structure in Iowa, where they had sort of the deep Precambrian red clastics overlying some of the younger Paleozoic rocks. So it is a feature seen from other impacts. So let's try to put it all together a little bit here. I know I'm probably throwing a lot of geology out at you. Here's what we believe to be the central crater area, and the north-south line, a slice across it would look like this. So this red line is the cross section that you're looking at here. So the structure, we don't have a vertical data point everywhere, but we have these three that have the colored bars here. Those are the ones we have geologic samples for. And then we have a few that are geophysical logs, but I want to focus on sort of just how the rocks I was just showing you fit in sort of the general map and scheme of things. That Jordan sandstone we were talking about is a nice, coarse, pure quartz sandstone, right? And it's generally traceable across the whole metro area, even all the way south into Iowa and Wisconsin and Illinois, as a fairly consistently thick, about 100 feet thick unit of quartz sand. And that's the yellow unit. It's yellow in this cross section. It's also yellow on the map here. And that overturned Jordan interval is sitting down here in elevation. So what we believe to be an ejecta flap has also possibly has come down into the crater area. And those deep rift Precambrian sediments are several hundred feet higher that we've noticed in the one with the shock quartz than they should be in the region. And so the grays are where the Precambrian rift sediments should be beneath the whole Paleozoic package. So you can kind of get a sense of this, the structure based on the few wells we have to work with and cuttings. We do believe we have one more overturned example just to the north here, and that is where there's just a thin set of cuttings, but it does look like there's Jordan at the bottom with St. Lawrence and the older units, the Tunnel City on top of that, and that occurs right here. So again, it's overturned and it's actually uplifted relatively to where those units should be. And then it's overturned and dropped down to where they should be over here. And then the central portion is actually uplifted. So we're seeing some patterns based on the limited amount of data to other crater structures, right? The area itself in pink is about a 4 kilometer in diameter area. This extra area is, it would be about an 8 kilometer diameter. And that's an area where we can still kind of understand the geology and map it out, but the structure of it appears to be different than what it should normally be. It's either uplifted a little bit or it's dropped down. So we still want to do more work to kind of analyze this area a little bit more to see if it really is, if those structures we're seeing are related to the impact event itself. So more work to do still, but when we do have as much as 575 feet of sort of a mixed sandstone, siltstone, shale sample that I've talked about, and that you know, it has similarities to what should be there in terms of the stratigraphy, but things seem out of stratigraphic order and overturned. And then those asterisks on this image are where the majority of the quartz sand that's shocked has been found. You'll notice that the upper sequence has been removed by erosion, which makes it kind of it makes it difficult to time when the impact actually happened, because the overlying sediments, this is several hundred feet of quaternary glacial sediment. So there's nothing to see if you went to the surface here. It's all buried by several hundred feet of quaternary sediments, even down at the river level. But because we don't have the overlying Prairie du Chien right on top of this sequence, it's difficult to really know for sure when it happened. Because the overturned beds happened to the Jordan sandstone, based on the samples we have, we believe that it has to be as old as, well, it does have to be as old, right, as the deposition of the Jordan sandstone. So it has to be at least 490 million years old. And we don't see any evidence of the Prairie du Chien carbonate, that tan carbonate that occurs all throughout this region as those blues and dark blues. We don't see any of that in the rock samples at the site. So that's another reason why we believe the impact to be late Cambrian, the age of the Jordan sandstone, rather than Ordovician. I guess, and I should just say that 490 million years ago is a long time ago, right? But it's a time when things looked very different on Earth. We were, you know, we were basically oceanfront property, and had, you know, basically a large beach setting in the Cambrian. We were close to the equator, had probably some nice weather, and so on. So as I've been going on here, the Pine Bend, we do think has overturned beds, has evidence of terrace brims or what was ejected and then dropped back down into the crater. So you can kind of see a model based on other craters, how that's happened. And what we do think we may have evidence of a central uplift, or those deeper Precambrian rocks are getting up close to the surface in what looks to be the center of our structure. So once you have a diameter and you have sort of, you know what rocks the meteor hit, then you can do all these fun calculations, right? You can estimate the size of the rock that came from outer space and hit Invergrove Heights. And based on these estimates and calculations, we believe that it would have been around 150 or so meters across, so basically the size of a football field or several football fields possibly. So this is on the range of some of the smaller craters on Earth, but this is still a big deal, right? This would have, you know, a space rock that large would have caused damage 30 times more powerful than the largest nuclear bomb. So you know, there's always so much more work we could do or we want to do. The map for Dakota County is being completed and will be out shortly this summer, we're hoping. But you know, we still hope to collaborate with other scientists and keep working on this crater. You know, just finding maybe analogs and models to some other sedimentary sandstone target rocks is one of the things we're working on. We definitely want to do some more investigation with sort of remote geophysical methods, maybe doing some gravity measurements and that sort of thing to sort of delineate the structure better. And you know, my pie in the sky dreams is to find some money to do some drilling into it, to get some more material to work with, an actual core where you're not just dealing with ground up bits of drill cuttings. Instead, you can see the structure of these features in a nice, you know, cylinder of core. You know, this is a map basically of all the water wells in the area, and I think it is worth noting that some craters are associated with different things in the groundwater. We have no reason to suspect this one is, but it hasn't really been looked into at all. So future groundwater analysis in the region, I think would be interesting to investigate. There are several hundred homes and businesses that have wells in the area that you can see there. All those black dots are all the wells in the area. So that's kind of the story of the Inver Grove site, and the regional geology. I guess I'm doing okay on time here. I'll go over a couple more slides. So if we look at how our structure compares to what's known globally, you can look at North America here. There are 60 craters documented in North America and 30 in the United States. And the size of these circles are based on the diameter, right? So the really big craters are the larger circles. Ours would fall somewhere between a small dot and a small circle. So it would be a pretty small dot in this region here of Minnesota that if we can get accepted and confirmed into the impact database. And you can compare it to, say, Chicxulub, which is down here on the Yucatan Peninsula. That was the 66 million year old impact crater that was the demise of the dinosaurs, right? And that crater, you can see, was giant, right? It's 180 kilometers across, or 110 miles in diameter, and over 12 miles deep. And it is the second largest crater, I believe, on Earth. And that one, clearly caused devastation and disruption, and what's known as the Cretaceous Paleogene extinction event, where 75% of plant and animal species on Earth went extinct. And that one is associated with shock quartz, a large gravity anomaly, and other impact features. And that one, again, if you can estimate, the energy produced by such a large feature with such velocity, I mean, you're talking the energy of millions of atomic bombs. If we compare up to Sudbury is just to the north of us in Ontario, or north east or so. Sudbury has ejecta deposits in Minnesota. So Pine Bend would be the first crater formation in Minnesota, but we do have ejecta from the Sudbury Basin in northern Minnesota near the Iron Range. And that event is older. It's considered 1.8 billion years old. It produced a crater about 150 miles wide, and it hit crystalline Precambrian bedrock. It's associated with shock features and shatter cones and other impact criteria. And it hit with such force and had such high temperatures that it melted the surrounding rock and produced a nickel, copper, palladium, gold sort of association within the crater. Around us, we've got Rock Elm, not that far away from us, just to the east in Wisconsin. The Rock Elm structure is around 445 million years old, or what's known as the Ordovician. So it's actually the age of what would be that Prairie du Chien rock that we talked about. And it is only about a 6-kilometer diameter structure. So it's on this order, the same size order as what we're dealing with in Inver Grove. The other one, the Decorah site that I mentioned, is just to the south of us in Iowa. The Decorah site is also about the same kilometer. It's about 5.6 kilometers in terms of scale. So similar to Pine Bend. It does disturb the Paleozoic strata, but it is also Ordovician in age and not late Cambrian. The Manson site in Iowa is located over here, just further west in northwest Iowa. That is a larger 35-kilometer diameter site, and it was once thought to be associated with the dinosaur extinction, but it did happen. It is known to be about 10 million years older than that event. But it's totally buried, and it's a totally buried structure as well. So I think I'll stop there and let you guys take the floor with your Q&A.
Okay, well, thank you so much. I have a few just basic geology questions. I apologize, these are my own questions, but when a meteor crashes into Earth, I'm assuming that nothing of the meteor survives because of the heat and the pressure. Is that right?
Yeah, no, that's a great question. From what I understand, when it's the larger ones, yes, you're right. Most of it just gets immediately vaporized and turned into dust or even smaller. But, small rocks, meteorites, do hit Earth, and some, one just hit New Jersey, I think on Monday, right? So the smaller ones that don't get burned up fully into the atmosphere, they don't create devastating craters. So some of the small ones can survive, the atmosphere, and some of the, signature of the meteorite can sometimes be found if you grind up these geochemical samples of your rock and look for the signature from a meteorite impact. So there's some fine geochemistry that could be done, but you're right, you don't generally see chunks of it or pieces of it in the sequence. You mostly just see what's known as an impact breccia, or just the breakup of all the existing rock that was there.
So what are meteors made out of? Like, when you're looking for this signature, how do you differentiate between Earth and meteor?
Most of them are just very high in iron.
Oh, okay. Okay, so I'm looking for some reassuring information here. How large does a meteor have to be to survive entry into Earth's atmosphere, and who is tracking this?
Those are always very interesting questions. And again, I'm not an expert on these things, but NASA or groups associated with NASA are tracking these things. There are billions of rocks floating around in outer space, right? And some are as small as fragments of dust, and some are really large. And so yes, they are actively tracking ones that may be in contact with Earth's orbit, right? That's something that they're looking for, but they don't claim to have eyes on all of them, right? There's always going to be other ones that pop up. And in terms of the size, that just, it can vary, right? And there's a lot, a lot of them likely just break up into the atmosphere, or burn up, right? There was one that happened in Russia, right, where it almost hit and then it burned up right before it hit, but created sort of a devastation in terms of the trees and the surrounding areas. So I don't really have a good answer for you in terms of size. I don't know, maybe you want to ask your question a little bit more if I didn't answer it that well. Go ahead.
No, you answered it. In preparation for this talk this morning, I was getting ready and I went out and filled up a bird feeder, and I thought, I wonder how many meteors are up there waiting to come down. So no, it's just a completely anxiety-produced question. And nobody can reassure me, I guess, about this. That's fine. That's fine. So,
well, I feel reassured. I think they've got eyes on the big ones. There's always an unknown, right?
True.
I think that the odds of winning the lottery are still lower than having a meteorite hit Earth. But
what are the rocks behind you? Are those pieces of meteorites?
No, they're not. Those are one's a piece of a conglomerate of Cretaceous age from Western Minnesota that has little shark teeth fossils in it. I just find it really amusing. I mapped Lac-Parle County not too long ago, so that's where that one's from. I actually can't, I don't know, I can't tell what direction to point, but the other one is a piece of what's of the Cambrian Ordovician boundary. So the top of the Jordan sandstone, it is a piece of the Jordan sandstone from so about, I don't know, 10 miles away from this impact site. Yes, we are. There's no exposures right near the impact site of these rocks, but you don't have to go that far away, a few miles or so to see them. So we are actively, trying to get out and look at the exposures and look for any additional evidence in terms of the timing of when this happened and any signature farther away in the rock record that's exposed today.
Okay, thank you. Earlier in your talk, you mentioned that, I think you mentioned that meteorites are associated with mineral and petroleum deposits. And I'm curious about the petroleum deposits. So you explained that the heat and the pressure can create different minerals and compounds, I think, but what is the petroleum association?
I don't know too many of the petroleum ones. The one that I do know is the one, I think it's called Red Wing in North Dakota. It hit and is associated with the Williston Basin, and it is associated with an oil deposit. But I think it's because the rocks already, are associated with an oil deposit. But they've got beautiful, deep seismic where you can see sort of the squiggly lines and a beautiful crater. And that's an example of one that's associated with oil and gas in North Dakota.
Okay. So we have someone who wants to know, they have kitchen countertop made of Southwest Minnesota quartz, and they're just curious if that is, I guess, what layer of rock that's in it, and is this a new thing that's now being used commercially, I guess?
So sometimes the industry has different names for the rocks, right, than the geologists use, but I would guess that you maybe have Southwest Minnesota. Well, it could be the Sioux quartzite, sort of a pink, almost sandy looking, but very hard rock. I don't know if they make countertops out of that. Otherwise, it could be like if it has a lot of bands and waves in it of both pink and black, maybe it's the Morton gneiss. Or it could be just another granite quarry down in Southwest Minnesota of a different rock type. All of those are known as, those are going to be the older geologic units in Minnesota, what we call the Precambrian, or things that are older than even the mid-continent rift that I noted. And those are rocks that I don't actually work on myself. My colleagues at the survey do, so they would know more about that than I would. But no, this particular feature, on the grand scheme of things, it's just a few kilometers and would have caused a lot of damage and environmental effects, right? But no, it's several hundred feet deep. We don't have plans to actively do any more drilling yet. And if we did any, it would just really be to learn more about the feature itself and know more about it. But no, there'd be no reason to really create any mining or quarrying near there. You just really don't do that unless the rock is really close to the surface.
Okay. We also have a question about fracking and what your thoughts are of it. What sort of damage does it do? Risks, benefits? Does your organization work with any companies that want to frack nearby?
Yeah, I haven't really had to work much with fracking at all. We don't do any fracking in Minnesota. That was something that was done right in the Dakotas and in other company or other states that had that have oil and gas. We don't have any oil and gas in Minnesota. Where we did sort of brush with it in the past was we have these nice mature quartz sandstones, 4 or 5 different layers of them, right? And those are often exposed near the surface. And there was mining proposed over the last during the frac sand boom, where they were looking to set up mines and basically dig out the quartz sandstone and use it for fracking in wells and other places. So that's really the only reason we were associated with it. And Tony Muckle, interim director of MGS, did most of the work on that. He's sort of the sandstone expert of Minnesota. So I don't have a lot more experience or know much more about frac. A lot of the mines that were proposed in Minnesota didn't actually go through. There were moratoriums in place. Wisconsin has more of the sand mining.
Okay. Do you know what was happening astronomically that there are so many craters in the 400 to 500 million years ago period?
Yeah, that's a great question. And something I maybe forgot to mention was that was a time, there definitely is a spike at that age interval. And so we just associate with must have been a time when there was a breakup of a large asteroid belt at that time. And then there was just a lot more debris that was close to Earth's orbit and then hit Earth at that time. Yeah.
Okay, how does the angle that a meteor hits the Earth at impact the findings that you might see geologically or even the shape of the crater?
It definitely should have an effect. Most of them we just have to sort of estimate, 45 degrees, something like that. It's probably not likely to come straight down, but it's usually at some type of an angle. The crater, out of all the 200 craters, you'd have to look at a few things. Did that hit hard? Did it hit a hard granite? It's going to form a different type of crater than if it hit a soft sandstone. So you kind of have to say, okay, well, you just have to model it after other craters. And I don't know much about, I'm sure others have looked at sort of finding features in craters where they've thought that maybe it came at more of an angle at this shape versus differently. I mean, it would likely change the orientation or the morphology a little bit of the crater if it had a very skipping shallow angle versus straight down. Maybe things wouldn't be quite so circular, they'd be more oblong. It's hard to say. And I know my feature, I think it's mostly that circular feature. It does have this sort of oblong oddness to it, but exactly what that is and how it's related is still questionable, or even if we should extend it a little bit more to the north is still a little questionable.
So I have a question about how you go about identifying these craters like you've recently identified at Pine Bend. And one of the things, what you said, you've looked at the different signatures of the different layers of soil, and they were not what you would have expected based on what's nearby. And so what I'm wondering is, if a meteor impact creates new compounds or new metals in the soil, when it happens, because of the heat and the pressure, wouldn't you expect to find a lot of that in that area, a lot of that new material that's been created? And wouldn't that be a better way of noticing it's a crater than having to look at the upheaval in the soil layers? Does that make sense? Okay.
No, absolutely. So part of the trouble we have is, you're right, usually what fills in that crater is all of what's called the breccia, or just the mix of all sorts of things, right? We don't have a core of our site to see that filling breccia, but we suspect it's there. But when you have rocks that are just ground up from drilling and comes up and out as just sort of loose sand grains, we've sort of lost all that sedimentary structure that would have been there. Maybe looked like a breccia, maybe looked like a mix of all sorts of different rock types that were associated with that site. So that's one of the reasons why we don't think we see that, which is where core drilling, if we can do more of that in the future, that would be ideal, to notice those things. But you're right, other craters are associated with a lot more of the fill of the breccia. You're right, yeah.
Any evidence that meteors are radioactive?
Boy, I don't know the answer to that question. I'd have to get on Google and start searching that one. I haven't thought about that.
Okay. Here's a great question. What can you say about the extraordinary fossil discovery record that appears to show the effects of the Yucatan meteor event? And are there any fossil remains at the Pine Bend event?
Yes, so we don't, that's the another one, an extraordinary fossil site is associated with the Decorah structure in Iowa. So, if you think about it, it's an ocean, if it hits, ocean sediments, it creates sort of a low feature in the ocean floor, right? And so it provides a space for fossils to sort of, get swept into and get preserved. And so these impact craters in marine settings are actually great places to preserve not only impact structure, but just fossils as well. We haven't seen any of that evidence. We just don't have exposures to really look for those things. And we also don't have core to see that kind of detail yet. So nothing with Pine Bend is associated with that. But, if we go based on that Cambrian Ordovician age, that isn't a time when there are other or many craters found at that time period. So many craters, not just Chicxulub, are associated with, very beautiful fossil localities. So yeah, that's an important aspect of them.
Can you tell us anything more about the largest crater that we have on Earth? I think it's South Africa, did you say?
Yeah, I haven't read up on that one. Verdiford, I don't know if I'm pronouncing it correctly, but that is the largest, and I think it's also the oldest. And no, I'm sorry, I can't tell you too much more about that. There's so many to keep track of all of them, and I've really only gone down this path recently in the last few years, trying to get up to speed on all these structures so I can have something to say. But that one I don't have a lot of information about. Sorry.
Sorry, it's all really interesting. What more can you tell us about the New Jersey impact that you just referenced?
That just popped up on one of my feeds. It was a meteorite, okay. Not an impact. I mean, in terms of, it was a piece of rock about this big that fell through somebody's house and hit the floor. Nobody, didn't hit anybody, but went through a house. And that's actually, it's pretty rare. So you hear reports about these things every so often, or have seen them, historically, but they were going to, and I think that was just on Monday. And the last I heard, they were going to, send it in and do some analyses on it to make sure it really was a meteorite and so on. But that was something that had happened just a few days ago in New Jersey.
Wow. If you could work anywhere in the world in geology, is there a certain spot that you would gravitate to just because it's fascinating geologically?
Boy, that's a hard question. I'm from Minnesota. My studies have taken me from southern Minnesota, Gustavus, all the way to Pocatello, Idaho. I did my master's thesis there. I worked on rocks in Nevada and came back here. I think Minnesota is a great place to do geology. Sometimes I wish there wasn't so many glacial deposits covering up all of all the beautiful bedrock. But, I don't know. I really enjoyed my time out west. I really haven't done much global exploration or global geology. So I can't speak to that too much, but I think North America is a wonderful place to do geology. I mean, Minnesota, we have, rocks as young as the glacial period, just 12,000 years old, all the way to, the oldest rock in North America, the Morton Gneiss, 3.6 billion years old. And that's right here in Morton, Minnesota. So Minnesota's got a great geological record. It's not continuous or complete, but it's expansive, and we have a lot of variety. So I really enjoy working in Minnesota.
Where can someone go? Where's the closest or several close by sites where someone could go and actually see a crater?
Yeah, that's a great question too. I've driven through Rock Elm in Wisconsin. You can drive through Pine Bend, just go south on 52. But you can't see it.
But you can't see anything.
No. You can see a few things associated. I haven't explored Rock Elm very much, but there's a park near there, and I think there's a few sites you can see, some tilted beds. It's not like a beautiful crater that you can see or by any means, but the Tacora structure is kind of set up similarly. There are rocks that I think you can see along the river and exposures, but the whole site is not fully exposed. I mean, you can't get any better than Meteor Crater. If you can get to Arizona and get to Meteor Crater, that's a wonderful place. It's set up, you can walk across the whole crater, you can see the whole thing. It's only about 1 kilometer across, so it's actually on the smaller side of these craters, but it doesn't seem small when you're standing right there. So if you can get to Meteor Crater, that's kind of the classic one.
Do you know if there's any recorded instances of a meteor causing a tsunami?
Like in modern time, I guess I'm not aware of that. I mean, we have to imagine that large tsunamis would have formed when marine impacts happened in the past. But in terms of a recent one causing a tsunami, I don't believe there's been a report of that in modern times.
Yeah,
I'd have to look into that one. Yeah. You can find a lot. You can Google these questions, and there's a lot about impacts on the web. I think a lot of people find it really interesting and fun to study.
It is. It seems almost supernatural. Just something falling from the sky and creating massive havoc on Earth, and it's unexpected. And I think that's what makes it so thrilling. Mm-hmm. Okay, so another basic geology question. All of these different layers of Earth that you've shown us pictures of, I mean, how do these things form? I'm assuming at the very bottom would be the mantle, if you could actually go that far down, but then what makes layers form on top of other layers, and why are the layers different? Why aren't they just homogeneous? It's all rock.
Yeah, well, it just has to do with the environment of deposition, and there's certain plates that make up the crust, right? There's either oceanic plates or there's continental crust plates, and that's sort of like the rigid lithosphere or the outer makeup on Earth, and those are several miles deep, and so we're not I don't really study anything deeper than the crust. There's other geologists that definitely do, but so sometimes crusts either come apart or plates either come apart or they're subducted. The continental crust that kind of makes up our area is considered the stable craton. It's sort of the middle of a big plate, so we're not really the mid-continent rift. Actually was a time when the plate tried to split apart but failed and came back together, but and that was in the Precambrian time. But what really makes the layers is basically when sea levels rise, or for some reason the plate subsides or sinks down somehow. There's different geologic mechanisms for that, but But when you can basically create accommodation space or a basin, which is usually through, marine oceanic conditions, is where you pile up the majority of sediment. And so that's what was going on here in the Paleozoic and the Cambrian and Ordovician. We were marine, we were ocean, right? There was likely a shoreline not that far away to the north of us somewhere, but we were basically covered in ocean water. And so it's just as sea level rises, you get more units stacked up on top of each other, and more formations. That's how sedimentary rocks form, and make those layers. And sedimentary rocks are a great record of past environments, of the geologic record of Earth. But there are, other rock types too, igneous, metamorphic rocks. Those are a little bit different, but those provide context. A lot of those are older, right? And basically as continental plates were sort of forming, there was a lot of volcanism and things going on, igneous activity that was sort of creating sort of those initial plates, and so on. But
so have meteors themselves contributed to the formation or evolution of our planet?
Yeah, I think that's what astrophysicists would say, is that the formation of our planet was just really just a large accumulation of a lot of impacts that happened over time. That's how our planet and our solar system formed as well. But again, that's getting out of my realm of expertise. But yeah, that's how it gets back to the creation of the solar system.
All right, we just have a few minutes left, and as we're waiting for some more questions to come in, is there anything else that you would like us to know about your organization or the subject matter for today?
I can't think of anything else. I could stop my screen share, but you can find me anytime through my email. We also have the website listed there. We sort of pride ourselves on being an unbiased source of scientific information for the state of Minnesota. So we work in conjunction with other state agencies and so on, but we just we're a resource to the public. And we like to do, we support stewardship of land, water, and mineral resources. So that's what we do. And once in a great while, you come across something, a new discovery that you got to follow up on, and it makes it really interesting. But for the most part, we just do some, what one would call routine geologic mapping. So
I think we have just one more comment here. Someone has said that for funding on delineating the pine anomaly, you may wish to approach the refinery and mention there may be reservoirs useful for CO2 sequestration there. And you would need to identify structure, closure, and reservoir properties. I'm not sure what that's referring to. There may be the anomaly of the Pine Bend.
Yeah, we don't really know the depths to our, to our structure at all. That's right. The deep, but we're really quite lucky that we have that many deep wells right in that area. That's actually pretty rare for the state. But yes, so the deepest ones we have are around 1,000 feet there, and so we don't know what's deeper. So that would shed light on the structure as well. If we could do more drilling. I don't know. If Pine Bed would be all that interested in hearing this. I haven't actually talked to anybody over there yet. I think everybody finds it interesting, but we have surveyed for carbon. We have done a carbon sequestration report on Minnesota's availability, but it's kind of deemed that we don't really have the space, the porosity, or the rocks for it, at least as far as we know. So.
Okay. Well, thank you so much. We are yet again, sadly, out of time. Thank you very much to Julia Steenberg, you, the audience, of course, for great questions, and the OLLI program. And I want to say a special thanks to Grayson Simmons for making sure that every time you click on your Zoom link, things work. To Steve Benson for finding and booking our speakers, and to Carmi Blyfus for keeping us organized. So this concludes our At the U at the Center series for this year, but please join us next spring for another fascinating look at what faculty and staff at the U are working on. Thanks again. Bye now.